Alright, so we're going to talk about different types of polynomials now. Okay, we've been focusing on quadratics, trying to get an understanding of quadratics, how useful they are in the real world. But now start to think about other types of functions, because other phenomena in the real world might be better expressed with a cubic instead of a quadratic, or might be expressed, for instance, we're doing area right now, correct? That's what that last question was about. Expressed with a quadratic. If I want to do volume, I want to maximize the volume of a box or the volume of some type of rectangular prism. Now I have to use volume as a three-dimensional concept, right? So I have to use a cubic to do that. All right. So maximizing volumes would be the need for another type of function. So we're going to start talking about the behaviors of these other functions and what they look like and how they relate to one another. And I think this is actually starting to be like a point in the course where stuff starts to get a little bit new. Okay, it's not as much old information or revisiting old information, and I think it's a little bit more interesting than maybe what we've been doing. Okay, but these are the things that we're going to try to talk through in the next day or so. Just general polynomial functions. Okay, we'll talk about graphing these. This is a topic that we want to be able to eventually be very skilled at, because when we're in Calc 1, we're in trigonometry, we're in Calc 2, whatever, when you see a problem, it's going to be a good skill to have, that if I can see a problem that provides me a function, to instantly, within, I'm going to say instantly, but maybe 1-2 minutes, I have an image in my mind of what that function looks like, what that graph looks like, okay? Because that might help me kind of work through the topic that I'm talking about in that Calc 1 course or that Calc 2 class. Okay, so that's kind of what we're trying to get at with this stuff. But we'll talk about how to graph these things. We'll talk about something called end behavior, which is a very important aspect of graphing functions. Kind of knowing where the arrows, when we graph a function, where we put the arrows on the end of the graph, okay? And how looking at a function can tell us that right away without even having to graph it. Okay. We'll use zeros. We'll figure out how zeros develop for polynomials, where we graph them, that kind of stuff. Then we'll talk about the shape of a graph near a zero. You guys remember hearing double roots last year? Okay, we'll talk about double roots, talk about triple roots, quadruple roots, that kind of stuff. It's referred to as multiplicity of roots. We'll talk about that and see what it means to us graphically. And then talk about local maximum and minimums of polynomials and how, not necessarily maybe how to find them, but how to know how many I'm going to have. Okay. What happens in calculus is we come up with a tool that allows us to find maximums and minimums much easier than any tool that we currently have. So let's talk about polynomial functions real quick. This is a rehash of what we've talked about in the past. I just put this slide in here because I think it's good to recognize this thing again. Get used to that thing. That definition there of what a polynomial is. That's the general form for a polynomial of degree n. Okay? So if we read that degree n, look at the picture here, look at the phrase, that is the term that n shows up in as just n, right? And the other ones have n, but they're n minus 1 or n minus 2 or n minus 3. N shows up right there, so that tells us kind of that when I look at a polynomial, the largest exponent that I see up there, because n is the largest one, right? Does that make sense, everybody? So if I've got n and then I compare that to n minus 1, well, n minus 1 is 1 less than n, correct? Okay? So n is the largest exponent up there. That tells me how I can classify that polynomial by what we refer to as a degree. Okay? We call that a degree n. Okay? If we just kind of jump real quick, I'll come back to this, but if I look at this slide here, maybe. This slide here, okay, this is the largest exponent, right? X to the fifth. We call that a fifth degree polynomial. Is that all right, everybody? A quadratic, what's the largest exponent in a quadratic? 2, right? So we call that a second degree polynomial. Okay? A line is a first degree polynomial. A horizontal line is a 0 degree polynomial. Does that kind of make sense? Sometimes called a constant polynomial. But working through this definition, okay, all of the a sub whatevers, a sub n minus 1, a sub 1, a sub 0, those are all coefficients of the polynomial. Okay? And they can be anything. They can be anything they want to be. Okay? A sub 0 is a special one because it doesn't have a variable term with it. We could, if we wanted to, do this. Put an x to the 0 with it. But what is x to the 0?
0.
Careful.
1.
It's 1. So we already got a sub 0 times 1 there. But we are starting with some n, and we are going to subtract values from this. So basically, and they don't have to be successive. So if this one's 5, this one doesn't have to be 4. Because my coefficient for x to the 4th could be a 0. Does that make sense? Okay? So you can skip over certain degrees because your coefficient could ultimately be 0. But the way this is set up is it's showing you that your polynomial is written in descending order. Remember hearing that phrase in Algebra 1? Alright, so some of the things that we talk about for polynomials, first thing you're going to want to do is reorganize things in descending order. And then you start classifying these polynomials and learning stuff about them if we do that. Okay? Since a sub n is the coefficient of the highest power, okay, so this one right here, it's the coefficient of the highest power, therefore it's called the leading coefficient. Okay? The leading coefficient. And really what we're interested in regards to that leading coefficient is its positive or negative aspect. Okay? For what we do today, we're really only worried if it's 2, I don't really care. I care that it's positive 2 or negative 2. Alright? And then a sub n x to the n, that's referred to as the leading term. Okay? So kind of put all these vocab words into play here with a specific function. We've got that one there. It says 3x to the 5th plus 6x to the 4th minus 2x cubed plus x squared plus 7x minus 6. The 3, 6, negative 2, 1, the 7, and the negative 6, those are all constants, right? Let's rephrase it. They're coefficients, okay? Negative 6 is the one that's constant, okay? The first term is the leading term, 3x to the 5th. That term, we call it the leading term because it dominates. It does so much more to my y value than the other 5 terms do combined. Does that make sense? Okay? And we'll talk about that here in a little bit. 3 is called the leading coefficient. It's degree 5. Sometimes, right, the further you get into a math textbook or math courses, authors start to get a little bit more fancy with their terminology, and they might call that a quintic polynomial, but most of the time we're going to call it a 5th degree. It's just a little bit easier to do that. So we have questions with that? Is that pretty straightforward? Alright. I'm going to skip over some stuff here. I added these to the PowerPoint a couple of years ago. I just talked about transformation, so we've talked about that in the past, so I don't want to do that right now. I want to talk about what we call end behavior of polynomials. End behavior of polynomials. And what end behavior is, okay, is what the graph is doing when x gets really, really large or x gets really, really small. Okay? So that's kind of what the next 4 or 5 slides are going to get at. But before we actually specifically talk about end behavior, I want to talk about what continuity is. Okay? Or what it means for a function to be continuous. We don't necessarily have enough mathematical background right now to actually give you a math definition of what it means to be continuous. You won't see that until, I would think maybe right now in calculus, the students that are taking calculus might be talking about what continuous means right now because they're just finishing up with limits. But we can still talk about continuous and what it means to us, we just don't have a math definition for it yet. But every line that you've ever come across has been continuous, and every parabola that we've come across so far has been continuous unless we restrict the domain. But not all functions are continuous. And what we mean by continuous means, if I were to put my marker on the furthest point to the left of my curve, so right there we're seeing right here, okay, bottom left. I want to trace the entire curve with my marker, okay? And if I can do that without lifting my pencil to move it to another portion of the graph, I would consider that function continuous. Okay? So if I look at this one, I get here, now to finish tracing the red curve, lift my pencil, move it up, put it back down, right? So because I have to lift my pencil here to finish tracing the curve, we would say that curve is not continuous. Does that make sense? All polynomials are continuous. So that's why it's saying here that not the graph of a polynomial function. Okay? So when I look at that and there's a break in it, I know it's not a polynomial because polynomials are not continuous. Or sorry, polynomials are continuous and this one's not. So we have, a lot of times here they're calling that a break, sometimes they call that a jump. Okay? But for the same reason, I come over here and I get to this spot here and it's a hole. So if I want to continue tracing this curve, I have to jump over that hole because there's not a point there and then continue tracing. That's a lot of times called point discontinuity. Okay? If something is continuous, you should be able to trace it, the entire graph, without lifting your pencil. Okay, you're fine. If I can't do that, we say that there is some type of discontinuity. Okay? Sometimes it's an asymptote. Okay? Sometimes it's a hole, like we see up there. Sometimes it's a break or a jump. Okay? And we'll talk about those things as we move on through the rest of the course. But the holes show up because we have division by variables, okay, or division by variable terms. Same thing for asymptotes. We have division by like a binomial or a trinomial or something like that. Okay, so polynomials don't ever have any of that kind of stuff, so polynomials are always continuous. Okay, so they're going to ask you to look at functions graphically and determine, is this a polynomial? Does it come from a polynomial or not? Okay. This first one here on the left, okay, another feature of polynomials is that whenever you graph them, they're always smooth, okay, meaning there's no sharp corners, like we said, there's no gaps or holes or anything like that. So if we look at that first one, there's a corner there, right? That's not very smooth. If I had this in my hand, I wouldn't want to touch that one because it's going to poke me, right? Okay, the other ones are smooth. They're not going to hurt me. Right, if I'm going to touch them, okay? So we've got the corners there, that's what we call that, in that first picture, and then we also have a cusp, okay? And you'll deal with things in maybe a calculus class that we deal with cusps, okay? And where they are going to provide us problems in mathematics, okay? We like to differentiate in calculus and find slopes of curves in calculus, and we can't do that at a cusp, okay? Because it just provides a problem for us. Okay? So that one on the left is not a polynomial, okay, because of those sharp edges. The other two, they are polynomials. They're continuous. You can trace them left to right and not have to lift your pencil, right? And they are smooth. Okay? Now, that does not mean that every single function that you see that is smooth and continuous is a polynomial. Does that make sense? Okay? Because I can give you sine of x, and that's not a polynomial function, but it's smooth and it's continuous. Does that make sense? Okay? These are just features of, when I know I have a polynomial, those are features that are going to occur. Okay? Alright, so now that's going to get talking about in behavior. And this isn't really a real complicated concept, all right, but I want to make sure that we do fully understand it. It's going to be asked quite a bit of you throughout quizzes and tests in the next couple of weeks. It says the domain of a polynomial function is a set of all real numbers, so we can sketch only a small portion of the graph. Okay, so when you see a polynomial, and we've done this for parabolas so far, we don't graph the entire thing, right? Because it goes on forever in the x direction, so we can not feasibly graph the whole thing. Alright, so to show that the graph is continuing the behavior that it currently has, don't we put arrows on the end of the graph? Okay, and that shows everybody that, you know, as you start choosing larger x values that are not currently on my graph, we have an idea of where our y values should show up. Okay, so for instance, if I have let's just go, just do a really easy one, y equals x squared. Graph that thing. Maybe I want to graph it between, 3 and -3. So that parabola is going to look something like that, right? Okay. But I usually put arrows on that to tell people that if you chose a number like 4, okay, then you know that your y value is going to show up here somewhere, right? We know visually, by putting those arrows on, that this graph is not, when I get over here to maybe like 4,000, my graph is not going to come back down. Does that make sense? Okay? We're implying that we know that this is the behavior, regardless of how far you go out on the x-axis, that behavior is going to be maintained. It's going to show the same pattern. Okay? That's what we refer to as end behavior. Okay? It says, however, for values of x outside the portion of the graph that we have drawn, we can describe what is going on with the y values. Okay? So the end behavior is ultimately, you're answering the question, what are the y values doing as x gets really, really, really big in the positive direction, or x gets really, 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 really big in the negative direction. Is that okay with everybody? Okay. And we put those arrows on there to kind of provide that understanding. Now what happens is that when we were trying to define and determine what the end behavior of a function is, the first term is really all we have to look at. There might be 30 terms in the function. But if I can look at the leading term, and the leading coefficient, and the leading degree, I don't need to worry about the other 29 terms. Does that make sense? And I'll show you algebraically why that's true here in a moment. Just some symbolism that we use to show that x is getting really, really big. Okay, we use the x and then the arrow, okay, and then the infinity symbol. And that means x is approaching, or x approaches infinity. Or you see there, they're saying x goes to infinity. I like to use the word approaches because that's going to be something that you use in calculus. Use that phrase with limits. And if we want to go to negative infinity, x approaches negative infinity. Okay? So what we're asking here, whenever we talk about end behavior, we're always using infinity, whether it be positive or negative. Okay? So if I look at that parabola that we just graphed on the board, and I want to determine the end behavior, I would say, as x approaches infinity, as I'm going that direction on the x-axis, where are my y values going? If I go out to 4,000, my y value would be really big, right? If I go out to 5,000, my y value even bigger. So as x is going to larger x values, what is y doing? Going to larger y values, right? So it's approaching infinity. So as x approaches infinity, y approaches infinity as well. If I go this direction, as x approaches negative infinity, okay, what is y approaching? Infinity. And the reason why in this one is approaching infinity is because no matter how big of a negative number I get, when I square it, that negative number becomes a positive number. Okay? So this degree here is going to be very important for us to understand end behavior, because if it's even, my end behavior is always going to be a positive number, isn't it? Okay? If that's a 4th degree polynomial, 6th degree polynomial, 12th degree polynomial, whatever, as we go this direction, we're going to go up. Okay? A positive number raised to the 12th power is still positive. But if I go in this direction, a negative number raised to the 12th power is going to be a positive number here, right? Okay? So that number right there is very important to us for determining end behavior functions. So that's kind of how we would deal with that with that curve. Okay, well, let's look at, maybe we have x cubed. I guess the next one there. Pretty simple function. If we think about what x cubed looks like, kind of looks like that, right? Okay. But as x goes that direction, as x tends to go to infinity, what are your y values doing? They're going to infinity as well. And think about what? If I take a large x value, if I take 1,000 and I raise it to the 3rd power, I've got 1,000 times 1,000 times 1,000 for my y value, right? It's a really big number, correct? A really big positive number. So as x goes to infinity, y goes to infinity. Now I do it this way. Let's say I get to negative 1,000. Well, what's negative 1,000 times negative 1,000 times negative 1,000? What kind of number is that? Negative. It's really big though, right? So as x goes to negative infinity, y goes to negative infinity as well. Okay? So there you're seeing maybe a little bit different in behavior than what we did in the last one. The last one said, and it's here is what's different. This one's still positive infinity, positive infinity. But this one, because it's an odd power, when you take an odd number of negatives, you always get a product that's negative, right? Okay, so that's kind of the end behavior for a cubic. Okay, now all cubics are going to kind of look that way. Okay, now and I don't really care. And I say all cubics are going to look like that, and I'll show you an image here in a minute with GeoGebra. But I don't, and we'll do some more math here to figure this out, but right now, I don't really care what is happening on the inside there. Okay? Basically from there to there, this thing could do several different things. Okay? It could do that, it could do something like that. Okay? We've got some options there, and that's all dependent on the remaining coefficients for like x squared and x and my constant for that function. Does that make sense? And those are the things that are going to kind of make this thing here either be kind of smooth or provide me those two maximums and minimums. A fifth degree polynomial is going to be the same kind of idea. But it's going to possibly do one more kind of undulation inside. Okay? We're going to have 1, 2, 3, 4 possible maximums and minimums. Okay? But this part here and that part there, the end behavior of a third degree, of a fifth degree, of a seventh degree, of an eighth or ninth degree, sorry, anything that's odd is going to have the same type of end behavior. Does that make sense? Now let's do this. Let's say that I have y equals negative, let's say x to the third. What's the negative? Think about transformation. What does a negative out in front do to an entire function? Reflects over the x-axis. So now the cubic, which this portion here was going that way, right? Okay. Now it's going to be looking like that. And this portion that was over here, so that's x cubed, right? So flipping over the x-axis should provide me that thing. Now did the end behavior change? Yeah, and the end behavior changes because now we're incorporating one more additional negative value. If I have x getting really big, okay, I'm taking a really, really big number and multiplying it by itself 3 times. So let's go to 1,000 again. 1,000 times 1,000 times 1,000 is a really big number, right? And it should be positive. But then I multiply it by 1 negative, my result should be negative. So as x goes to positive infinity, y goes to negative infinity. Okay? Now if I go negative infinity over here, as x goes to negative infinity, let's say I have negative 1,000. Negative 1,000 times negative 1,000 times negative 1,000 gives me a negative number, right? But then I've got this additional negative, which now just basically took these 3 negatives and turned it into 4 negatives, right? Well, that's an even number of negatives, so what happens? It becomes a positive number. So as x goes to negative infinity, y goes to positive infinity. Okay? So as we are doing end behavior, the things that matter the most, okay, of any polynomial, let's just say I write y equals, and let's just go a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2, all the way down to our constant. The things that matter the most to us right now in end behavior is that n and the plus or minus that shows up right there. Okay? And if we understand the relationships between those things, that's going to give us the end behavior. Okay? None of this other stuff here, no matter what those are. And like I said, if you have a 30-degree or 30-term polynomial, those 29 things are not going to matter. Okay? They have very minimal impact on what our end behavior does. Okay? And this is the logic or the reason why. If I give you, what time is it? Okay,
9:50.
Right. If I give you a function that looks like this, let's say that our function is 2x to the 4th plus 6x cubed plus 4x squared plus, let's just go x plus 5. Okay, if that's my function, okay, hopefully we understand that this graph, if we're to graph this, okay, the end behavior, okay, as x goes to infinity, okay, just look at this thing right here. As x goes to infinity, okay, x is 1,000, multiply it by itself 4 times, and then multiply it by 2, what kind of number are you going to get? Positive. So as x goes to infinity, y goes to infinity. Okay, so my end behavior is going to be out there somewhere. Okay, as I go to negative infinity, as x goes to negative infinity, What is that y value going to do? Well, a negative number multiplied by itself 4 times gives me a positive number again, right? Double it, just gives me a bigger positive number. So there's my end behavior, so it looks like that. Now again, these things here, that term, that term, that term, and that term, those 4 additional terms are going to kind of dictate what happens on the inside. Okay? Might do something like that. It might do something like that. Might be kind of parabolic looking. You know, sometimes we see them look kind of like that. But I don't care right now. I'm only worried about end behavior. And these things don't affect end behavior. And I'm going to show you kind of why they don't affect end behavior. I want to rewrite this thing. Okay? But I'm going to rewrite it through factoring. So I'm going to factor out the leading term out of all of these things. Even though that leading term doesn't show up in there. Does that make sense? We're still going to factor it out. And the way we can do this, and the reason we can do this, is what operation are we talking about when we say factor? Well, when I put this back in, I'm multiplying, right? So when I'm taking it out, I'm dividing. Okay? So I'm going to rewrite this just by factoring out 2x to the 4th to every term. So I'm going to divide every term by 2x to the 4th. So if I do that, 2x to the 4th, right there, that's going to give you 1, right? So put 1 right there. Divide by 2x to the 4th. 6 divided by 2 gives me 3, so I got 3. But now where does... I've got these 3 are going to cancel out with 3 down here, right? Now I'm left with a variable of x in the denominator. Does that make sense, everybody? Okay. We're going to do that for every one of these. 4 and 2 cancel out and give me a 2 up top. But now x squared divided by x to the 4th gives me x squared down bottom, right? Dividing this one by 2x to the 4th just gives me the x's cancel out, or 1x cancels out, so leaves me 1 up top, and what, 2x cubed on the bottom. And then the 5 just leaves me as 5 over 2x to the 4th, nothing cancels out. Alright, so that's just dividing out the leading term, not a greatest common factor, because 5 didn't have this factor in it. But if I were to distribute this back through, I should get back to exactly what I started with. Does that make sense? Okay? Now here's the logic. Here's why I did that. When we talk about end behavior, we're worried about x becoming a very large number, right? Okay? Well, let's take x to be a very large number. Let's say that x is 1,000,000. Raise that to the 4th power. Okay? So what's going to happen, I think I get 24 zeros there when I do that. Okay? Because when I multiply 1,000,000 times 1,000,000 gives me 12 zeros, right? And then 12 zeros times 12 zeros should give me 24 zeros. And then multiply that by 2. So that's a pretty big number, right? Would you agree with that? Very, very large positive number right now. Okay? Well, when I plug in x to be 1,000,000 here, I get 1 there. But what's 3 divided by 1,000,000? What kind of number is it? It's very small, isn't it? Isn't it 0.000003? It's very close to 0, right? And think about what x is. This is actually a really tiny number in compared to where x is going, right? X is going to infinity. Okay? So imagine, you know, maybe this becomes 1 billion. Okay? Or maybe it becomes 1 trillion or something like that. This number gets closer and closer to 0, right? So that number right there is very negligible. Okay? Very small amount. 2 over, now 1,000,000 squared, well that's, like I said, it's a 1 with 12 zeros. I'm not going to write that, but 1,000,000 squared, that thing goes, or gets very, very close to what number? 0. Well, 1,000,000 squared gets closer to infinity, right? But 2 divided by that, 0. If I take $2 and divide it amongst 1,000,000 people squared, nobody's getting any money, right? Okay? So this thing goes to 0 as well, just a lot quicker than this one did. Well then, this one here, 1,000,000 cubed, is going to 0 even faster, right? And this one here is going to, I'm not going to write it, but this one goes to 0 even much faster, correct? Okay? So, ultimately, like I said, these values are negligible. They're zeros. Okay? 1 plus 0 plus 0 plus 0 is 1, right? So, when I'm talking about my end behavior, when x is really, really big, these numbers do not impact. They're decimals and very, very, very small portions of decimals for what this number here is providing. Okay? So that is what is the reason behind looking at the leading term, and the leading term tell me what the end behavior does. And I don't have to look at the other 5 or 6 or whatever additional terms we have, okay? Because that proves to us that X gets really, 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 really big. The leading term dominates everything, okay? We will talk about some more of this stuff tomorrow.